that before. So we need to talk about solution concentrations, and this is a review of Gen Chem 1. What a solution is it's two or more things that have been tossed together and it makes a homogeneous mixture. So solutions are homogeneous mixtures. That's it. We tend to think of, I'm going to draw a picture. Here's my beaker of my solution. Okay. The thing that's in there in large amount, that is the solvent. So I know we talked about it in Gen Chem 1, but you're going to want to get it under your belt again. The thing that's already in the beaker is the solvent. And the thing that we're adding to the beaker is the solute. And a lot of water is a great polar solvent. And so a lot of times our solvent is water. If our solvent is water, that means that it's an aqueous solution. And we use the symbol AQ to kind of show that in an equation setting. Very good. So there's this classic sort of problem that's going to be associated with this part where you take a solution and you have to describe how concentrated that solution is in different units. And so we're going to talk about different units. Most units are a given amount of solute per a given amount of solution. And remember, solution is the whole thing. But we are going to dabble with this new sort of way to express the solution concentration, and it's in terms of solute per solvent. Okay. So there's a subtle difference. Solutes both in the numerator, but it's per solution in one case, and the other one is per solvent. So that's my asterisk down here. Kind of got this. I don't know if you can move that. Anyway, that's cute. All right. So generic terms, we're going to talk numbers here in a minute, but some says it's concentrated. That means it has a lot of solute in it. If it's diluted, it means that the amount of solute is pretty good. Those are just generic terms. Again, I think we kind of covered this in Chem 1. These things we covered in Chem 1, what they have to do with, let's see how it says. Anytime you see fraction, like mass fraction or mole fraction, that is parts per one. I guess I didn't want to do the fraction part. So that's parts per one. Mass percent or mole percent are parts per 100. So volume fraction would be parts per 1, and volume percent would be parts per 100. Grams per liter, okay. Moles per liter. What all of these have in common, it is amount of solute per a given amount of solution. Solution is the whole mixture. That's what they all have in common. So we're going to kind of revisit those a little bit, or some of them. The other one, and this drives me nuts, it totally does. They sound so similar, but they mean, and they are similar, but they mean different things. The molarity, we've talked about, that's moles of solute per liter of solution. Mole solute per 1 liter solution. You guys got that down. Molality is very important, and that's moles of solute again. But in this case, it's per kilogram of solvent. Drives me nuts. Molarity and molality. You'd think they could come up with something different. They both have moles of solute in the numerator, but the denominator is different. And they both are M's, but molarity is a capital M and molality is a lowercase m. Are you serious? Yes. So the fact that
These two right here, the grams per liter and moles per liter,
the fact that in the bottom they have liters, one of the things about liters is your volume actually will change with temperature. Water is that funky thing that actually, let's see, water will swell, it becomes, no. So as water cools down, let's do it this way. As water cools down, it becomes more and more dense, liquid water. That's normal, okay? But there about 4 degrees, it has its maximum density, and we talked about water, and then actually as it solidifies, when we talked about recently, I think, as it solidifies, it bloats out. So we have more density. So anyway, your volume is running target, so it's temperature dependent. This guy down here, not temperature dependent, because the mass of solvent won't change with temperature. Okay, so let's kind of look at a few of those. And I told you fraction means parts per one. So mass fraction means the fraction of a gram of component A, so mass fraction of A. The fraction of a gram of component A you have in 1 gram of the mixture. It's parts per one.
grams of component A per grams of the whole mixture, the solution.
So when we work problems, we're going to have to visualize the component and then visualize the thing the component's in. The thing the component's in, goes in the denominator. We can take mass fraction and get it to mass percent simply by multiplying by 100. Because mass fraction is parts per one, and mass percent is parts per 100. So you just multiply by 100.
But what mass percent means is, so it looks like this. Mass of component A divided by mass of solution or mixture, which is mass fraction, right? Times 100%. That will give you percent of A.
All right. Mass fraction. Both mass fraction and mass percent are unitless because you're taking the relative amount of the component divided by the relative amount of the mixture. So your units cancel. So it's unitless.
You need to know to be able to unpack numbers.
So if someone gives you a mass fraction of a component in a mixture or solution, and they say that mass fraction is 0.159, we talked about unpacking in Chem 1. What that means is you have 0.159 grams of that component in 1 gram of the mixture, in 1 gram of the solution. That's unpacking. We could unpack that
15.9%, which would be actually the same as the mass fraction, 0.159.
15.9%, what does that mean? Unpack it, that means you have 15.9 grams of the component in 100 grams of the mixture of the solution. So those are unpacked.
See, these go fast.
All right.
Now, one unit we haven't talked about yet, we've talked about parts per 100, but parts per million, abbreviated ppm.
Parts per million. In environmental samples, oftentimes we'll be looking for pollutants in parts per million. It's relatively dilute. Okay. So that would be what?
It could be the milligrams, or excuse me, it could be the grams of A in 1 million grams of solution.
Well, that's what that's. Grams of A in 1 million grams of solution. So if you have
Mass fraction, you can get to parts per million by multiplying, not by 100, but multiplying by 1 million. So
So you can take mass fraction, multiply by a million, 10 to the 6, and get parts per million. Now here's a trick for you, and the way this works is if water is your solvent and you don't have much solute, if your solute is on the light side, which means it's a dilute aqueous solution, then if you have the parts per million of a component, because it's dilute and because it's aqueous, then that's approximately equal to milligrams of that component per liter of solution. And I didn't do the proof because I just think it's so interesting. It has to do with the fact that the density of water is 1.00 grams per milliliter. And you track it down and you end up with milligrams per kilogram, which is parts per million. Well, it's not that hard. Actually, 1 liter of solution weighs about, will weigh 1 kilogram. And there's your factor of 6. So parts per million for dilute aqueous solution is the same thing as milligrams per liter. If you see milligrams per liter, again, unpack that. That means milligrams of solute per liter of solution. All right. Right. So mass fraction was the mass in mass in 1 gram. Mole fraction looks like this. Basically, you have a solution and you count up the total moles of everything, the total moles of all the solutes and the total moles of the solvents, and that goes in the bottom. Then you stick the moles of your component of interest in the top, and that will be the mole fraction. Mole fraction is denoted with an X and a subscript of what the component of interest is. So you would read this as, this is the mole fraction of A. Mole fraction. The moles of the component A per 1 mole, total mole of everything. So again, we have the relationship between mole fraction and mole percent, like we did between mass fraction and mass percent. If you have the mole fraction, you simply multiply by 100 to get to mole percent. Groundhog's Day, he saw his shadow, so who knows? But anyway. So grams per liter, I think we talked about that in Chem 1. That's the grams of solute per liter of solution. And what we end up doing is taking the mass of your component divided by the volume of your solution. Might not be a liter. We'll do an example here in a minute. And that will give you grams per liter. So here's our problem. For working these, and it's a way of stalling, I know, but I am notorious for, I like to draw a beaker. I can't remember my solution keys. I think I drew beakers. Maybe not. So question mark, what is the concentration in grams per liter of this solution? And it says what we did was add 32.3 grams of sucrose, and the total volume of the solution was 225 milliliters. So here in a minute, all you're going to see me do to get grams per liter is basically take those grams, divide it by those milliliters, and then remember you need to fix the milliliters to liters. That's all I'm going to do. So 32.3 grams of C12H22O11 per the volume of the solution, 225 milliliters. So do you guys remember what that next term will be to have milliliters canceled? We left the liters in the denominator. 1,000 milliliters over 1 liter. Yep, 1,000 milliliters of solution over 1 liter of solution.
And now our milliliters cancel. We have units of grams per liter, which is perfect. And then how many sig figs? Fingers?
Very good. So 144 is around 3 sig figs. I would probably write it like this bottom one down here. 144 G/L grams per liter, and then the component name is C12H22O11. Cool.
I swear that I pulled these right from my Chem 1 because it just seems familiar to me. Because the next part seems familiar. We're going to take the same solution and we're going to change it up, and we're going to come up with the molarity of this solution. So remember that molarity is moles of the solute per liter of the solution. So for instance, and we're going to come back to that sucrose problem here in a minute, but for instance, if you need to unpack this, and I already warned you that we're going to be dealing with molality too, which is a lowercase m. If you need to unpack that, that means 3.0 moles of HCl per 1 liter of solution. That's what that means. All right, there we go. So we're going to look at that sucrose solution in the previous example. And what we did before was we took what the mass, or the grams, divided by the milliliters, okay? And we could do that again, but I'm going to piggyback. At the end we had grams per liter, and if I want to get, how do I get from grams to moles? Molar mass, yep. So all I got to do is introduce the molar mass. And I don't always put molar mass calculations on my slide, but kicking off Chem 2 right anyway. So the molar mass of C12H22O11 is this. So 12 times 12.01 plus 22 times 1.008 plus 11 times 16.00. So the molar mass of sucrose is 342.30 grams per mole. So as you work a problem where you're supposed to have the same solution in different concentrations, feel free to piggyback off of a previous solution concentration. So we came up with 144 grams per liter. So being explicit, we have 144 grams of C12H22O11 per 1 liter of solution. So how can we use molarity to have grams cancel, be left with units of moles in the numerator? You guys know. Yeah, exactly. 1 mole over 1 mole over 342.30 grams. Now, there's a good chance if I was working this problem, I probably wouldn't put the formula, the chemical formula. I probably would not, because we're only dealing with one solute. So, but it's not wrong to put it. So how many sig figs? 3. I'm liking 3. So around 3 sig figs, you get 0.419, and so explicitly it means 0.419 moles per 1 liter, or you can just simply write 0.419 big M, meaning molar, of C12H22O11. That's it. A feel like that's kind of Chem 1 stuff, which is not bad.
It is, but still gotta go slow.
Right? Okay. So, now this is new to Chem 2. Hey, that rhymes. So, molality, lowercase m, like I said before, means moles of solute, again, like we have with molarity, but the denominator is kilograms of solvent. So the weight or the mass of the solvent in the denominator. So the way this works is if your solvent is water, and if you don't have much solute in it, for dilute aqueous solutions, as it turns out, molarity is approximately equal to molality. And again, that has to do with the fact that water has the density it has. All right. So I think I mentioned this before, that anything that has volume in the denominator, like grams per liter or moles per liter, it is temperature dependent. But molality, which has kilograms of solvent in the denominator, is not dependent upon temperature, so it's independent, which can be nice. But molarity and molality. And I try not to get mixed up as I'm up here trying to talk about them. But we have two solutions. This is potassium chromate. And in this case, of course, this is called a volumetric flask. And the way volumetric flasks work is there's a red line up here, you probably can't see it, that now this is a volume of, the solution volume is 1 liter. And so what they did to get 1 molar, or excuse me, 0.1 molar, was to take what, 1.94 grams of the solute and dissolve it in 1 liter. In this one, they had to take 1 kilogram of solvent. The solvent is water. 1 kilogram of solvent is actually 1 liter of water. Well, it depends upon the temperature, I guess. So they took 1 kilogram of the solvent, and then they added the 1.94 grams of K2CrO4. It's potassium dichromate. No, it's potassium chromate. Of potassium chromate. So that's why it went up a little bit above the calibration mark. So which one's more dilute if they both have the same mass of solvent? Which one? The first one, the one less one's more dilute, and it is more dilute. So that's the kind of thing that you're going to be kind of wrestling with. Okay. So we're going to work this problem here. I think I'm going to draw it on the board so I can kind of refer to it. So here's my beaker of concentrated nitric acid. Now the thing is, with regard to acids, even if they say concentrated nitric acid in this case, it's not 100% HNO3. It's HNO3 as strong as you can get it in a solution of water. So nitric acid, I'm going to go ahead and unpack as I go, if that's okay. So the 70% HNO3 by mass, that means that there are 70.0 grams of HNO3 in 100 grams of the solution. So this solution is HNO3 and water. Well, before I leave that, so if that's the case, how many grams of H2O are there in 100 grams of the solution?
30.
30. Yep, there are 30. Does that make sense? That might be helpful. So the grams per 100 grams of solution. The density is given here. So I'm going to use the symbol rho. Density is equal to, I'm going to unpack that. One of the things we talk about density is you've got to be careful grams of what. So the density is 1.42, remember that's grams of solution per 1 milliliter of solution. Cool. We got those two things going for us. And it gives us a temperature, and we won't need to use that in our problem. So we're supposed to knock out question mark. And I'll go ahead and as I pull them, I'll say what the units are. So calculate the molarity. So what is the molarity? That's moles of HNO3 per 1 liter solution. That's the molarity. Question mark. I'll put a big M there for molarity. Molality. Calculate the molality. Well, that must be again moles of HNO3 per 1 kilogram of, in this case, water, 1 kilogram H2O. Don't get caught in, it's not 1 kilogram of the solution, it's 1 kilogram of the solvent. That's our second one. Mole fraction. So, question mark, mole fraction. Remember the symbol for mole fraction is X. And I'm going to go mole fraction of HNO3, so I'll put HNO3 down here. What that means is we're after another ratio that, again, wow, we have a lot of moles of HNO3, don't we? That will be the ratio of moles of HNO3 per the moles of everything. The moles of HNO3 plus the moles of the H2O. Right? So these three solution concentrations, it's like a puzzle. But do you see where in my comings and goings, if I can come up with the moles of HNO3, that I'm going to use for all three of those solution concentrations. We're going to work this problem twice. And see, it seems like, have we, in Chem 1, did we talk about a basis? A little bit, yeah, when we did the combustion analysis. Remember, the basis was 100 grams of the compound? We're going to do a similar thing. We're going to pick our basis. And our first basis, I think we're going to go with 100 grams of solution. Okay, and can you see why I would do that? And I say consider, that's my basis. Consider, or I say basis, 100, I'll go ahead and put 100.0. So I have 4 sig figs, 100 grams of solution. Okay. The reason I would do that is things start to fall in place if this is my basis. For instance, if I have 100 grams of solution, how many grams of HNO3 do I have? 70.0. If I have 100 grams of solution, I've got 30.0 grams of HNO3. Dang, based upon that grams of HNO3 on my basis, can I come up with the moles? Yep. The next slide, we're going to knock out molar mass, so we can get the moles. Based upon that mass, do you see where I can actually use this ratio to get to volume? Okay? And that's actually how I'm going to knock out that denominator. So things start to fall into place. So let's see. Molar masses of the solvents, the solute and the solvent look like this. You probably already know the molar mass of water. But the molar mass of HNO3 is 1.008 plus 14.01 plus 3 times 16.00. So the molar mass for the solute is 63.02 grams per mole. And for the water, we're going to take 2 times 1.008 plus 16.00. And that'll give us 18.02 grams per mole. Like I said, we're going to work this twice. So if we take as our basis 100.0 grams, then like I said, based upon the original information given, what falls into place, the reason we're doing that is bada boom, we know the mass of the solute and the mass of the solvent. Isn't this weird? Is this weird to you? It's like we usually think as the solvent is the thing that's in greater amount, lesser amount. Okay. The next one we're going to do here right quick before we leave is we're going to take it instead of 100 grams, we're going to go with regard to volume of the solution. 1 liter. So, I told you a minute ago, if you have 100 grams of the solution, we can use density to knock out volume. So here we go. Our first term is going to be the basis, 100.0 grams of solution. I usually put that over 1. And then can you see where if I want grams of the solution to cancel, I'm going to have to what? Flip this, aren't I? So if we use the flipped version of density, we have 1 milliliter of solution over 1 milliliter solution over 1.42 grams of solution. Now we need to get to liters. And the reason we're doing that is so we can go ahead and knock out molarity. So to get to liters, it looks like this, right? 1 liter, oh, I thought I got to liters. I see here, I didn't, but you know. I left it in milliliters. I guess we're going to fix it in a minute. But if you already did it, that's fine. So how do we get to the moles of HNO3? What's our first term? Going to be that 70.0 grams. And then we're going to use the molar mass. So it's the flipped version of the molar mass. So 1 mole over 63.02 grams. Looks like we're allowed 3 sig figs. So moles of HNO3 are 1.11 moles of HNO3. Again, if I label, like this blue label is here, if I label it up here, I may not include HNO3 in this, just because I labeled that step. So what's our starting mass for our H2O?
730.
Yep.
Okay.
30, very good. 30.00 grams, and we use the flipped version of the molar mass for water, so 1 mole over 18.02 grams. Grams cancel, we have moles, give us 3 sig figs, so you're looking at 1.66 moles of H2O. By the way, you might be like, well, I don't need moles of H2O to get to molarity. Okay, but I do need moles of H2O down here to get to mole fraction. So this is kind of developing some puzzle pieces. All right, so knock out molarity. So since we didn't fix the volume to liters, we're going to have to fix that here. So if we put that 1.11 moles of HNO3 over the 70.4 milliliters of solution, now if we fix milliliters, we can put 1,000 milliliters over 1 liter. And then round to 3 sig figs. So that gives us a molarity of 15.8. And that's moles of HNO3 per liter of solution. Again, if you just put 15.8 big M HNO3, that's fine. Cool. Well, that's 1 of 3. So this one, can you kind of see how next I'm going to do? We're going to take that same moles, which was that 1.11 moles, and we don't have a kilogram of water, but by golly, we got 30 grams. Okay, so we're going to use that here. So to get to molality, it's the moles of solute divided by the kilograms of solvent. The solvent is water, and on this basis, we had 30 grams of water. So kind of like we fix milliliters into liters, we have to fix grams into kilograms. How can we do that? Put 1,000 grams on top and 1 kilogram on the bottom.
1,000 grams of H2O in the top, 1 kilogram in the bottom.
So now if we do kind of a quick check of what cancels, our units of grams of H2O have canceled, and we're left with units of kilograms of H2O, which is perfect. So again, moles of moles of HNO3 per kilogram of H2O. 3 sig figs, that gives you the molality of 37.0. Cool. Last but not least is this mole fraction. So this one's not too bad. We just have to revisit earlier where we had the moles of HNO3, which is 1.1, and divide by 1.1 plus the moles of H2O. Yep, so it looks like this. 1.1 moles of HNO3 divided by 1.1 plus 1.66 moles, total moles in our solution. Give ourselves 3 sig figs. And I get a value of 0.401. And remember that mole fraction and percent are unitless. There's no units there. Well, percent is units of percent, I guess. All right. That's it, man. So let's see, what if we changed it up? And this one's harder for me to wrap my mind around a little bit. But if we focus on, to me, the key here would be to this guy right here. If we go with 1 liter of solution, okay, then we can go ahead and get the mass of the solution. And if we have the mass of the solution, we can use these ratios to get to the relative masses of the solute and the solvent. So getting the mass of the solution using density, if we're going with 1.00 liters, that's our starting point, 1.00 liters. Okay. And do I convert to milliliters next? I kind of do my 3 terms up there. I don't know what order you put them in. But to use the density, which is grams per milliliter, we have to get that those liters to milliliters, which that last term does. But the second term is the density, 1.42 grams of solution per 1 milliliter, and this kind of fixes the whole milliliters to liters thing. So bottom line, liters cancel, milliliters cancel, left with grams of solution, which is awesome. Giving us 3 sig figs, you're looking at 1,420 grams of solution. Now, if I look at what I'm trying to do here, I don't have grams of solution as anything in the denominator, but I'm going to use it here in a minute to get to the relative masses of my solute and solvent. So I can use either one of these ratios or to get to the mass of the HNO3. This one, I guess, this one, HNO3. So if that's the gram of solution we have, then if I just don't even flip this, if I just insert that there, 70.0 grams of HNO3 per 100 grams of solution. Grams of solution cancel, we're left with grams of HNO3. Round to 3 sig figs, voila, 994 grams of HNO3. Now, this is a different basis, right? So these won't specifically match up with our previous bases, but relatively speaking, we should get the same numbers. So if we do a similar thing for H2O, we have our 1,420 grams of solution times 30 grams of H2O per 100 grams of solution. Round to 3 sig figs, we get
426 grams of H2O. So now the fog is kind of lifting a little bit. You can see now we have the mass of your solute and your solvent, and of course we can use the molar masses to get to moles, and then we're kind of on our way to knocking out the problem. So we did the molar masses before, so with that mass of HNO3 to get to molar mass, to get to moles, it's a molar mass. So 994 grams of HNO3 times, 994 grams times 1 mole over 63.02 grams, round to 3 sig figs. And we have 15.8 moles. So we're getting closer to knocking out our answer. This one just seems like more work. Maybe it just feels like more work because we did all that work before. To get the moles of H2O, we're going to use the mass of H2O we had on the previous slide, which is 426 grams of H2O. Multiply it by 1 mole over 18.02 grams. Give us 3 sig figs. Relatively speaking, that's 23.6 moles of H2O. And I think that's it. I think we're done. We're done with our puzzle pieces, ready to assemble them, I think. So this one's pretty easy because our basis was 1 liter of solution, right? So all we got to do is take those moles divided by, 15.8 moles divided by 1.00 liters of solution, because that was our basis. That's probably the easiest. Give yourself 3 sig figs and you get, not so surprising, 15.8 moles per liter, 15.8, moles of HNO3 per liter solution. Let's see, the next one. We're going to use the same numerator, but now we need kilogram of H2O. Now remember we had grams of H2O on our previous slide. So that looks like this. Again, 15.8 moles of HNO3 divided by 426 grams of H2O from the previous slide. So give ourselves 3 sig figs. Oh, wait a minute. We need to fix our grams, don't we, into kilograms. So to do that, we're going to put 1,000 grams over 1 kilogram. Give ourselves 3 sig figs. And the molality is 37.1. Over here, I had 37.0. You might be, well, I'm Mrs. Snipes. Which answer is the best one? I don't know. I'd have to track it down. They're both definitely acceptable in my book. Then the last one, we're not too far from either, because the mole fraction, we just have to go back to a previous slide. This will still be the same number in the numerator. In the denominator, we'll put this number plus the moles of H2O. So it looks like this. So we have 15.8 moles of HNO3. In the denominator, we have that 15.8 again, plus the moles of H2O, which was 23.6, the total moles. Give ourselves 3 sig figs. And I get 0.401. Sometimes I'll be grading your homework and I'll be like, well, that's not exactly what I got, but I see it's a valid, if it's close, I'm like, I think it's probably just one of those things. Okay, mole fraction. Dun, dun, dun. We did it, 40 slides. Right? Anyway, so have a great weekend.